Hi, my name is Dr. English, and today we're going to be talking about chemical formulas. Specifically, we're going to focus on oxidation numbers. So in this tutorial, we're going to be looking at what are oxidation numbers in ionic compounds, oxidation numbers in molecular compounds, looking at the rules for oxidation numbers in free elements, oxidation numbers in neutral compounds, oxidation numbers in ions, some common ions and exceptions, and finally doing a little bit of practice at the end. So what are oxidation numbers? Well, an oxidation number is basically a number assigned to an element in a chemical compound that represents the number of electrons lost or gained, depending on the situation, by an atom of that element in the compound. We can assign numerical values to real and apparent charges by using a set of numbers known as oxidation numbers, or oxidation states or charges. Oxidation numbers can be positive, negative, or zero. Oxidation numbers or charges are found in the upper right of the element box of the periodic table. So if we look at chlorine right here, while potassium only has one oxidation number, chlorine has a series of numbers listed in the box associated with it. Now let's look at oxidation numbers in ionic compounds. Now, if we remember back to ionic bonding, we know that an ionic bond is made up of a metal ion, typically, and a non-metal ion, and the metal ions are typically going to want to become positive ions and lose electrons, while non-metals are going to typically want to gain electrons. So when we look at oxidation numbers here, this is what's really showing us how they're going to come together. So positive metal and negative non-metal ions will combine to form ionic compounds because opposite charges attract. So here we have an image of sodium right here, and we know that sodium is Na with one valence electron. So when it loses that one valence electron, it'll become an ion, a sodium ion, with an overall charge of +1. And meanwhile, chlorine, on the other hand, is Cl with 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. It will become an ion when it gains an electron to complete its octet. So the positive ion here and the negative ion here will ultimately come together to form a much more stable compound, as we say down here, of sodium chloride. And remember, this is all about stability. Sodium by itself is very reactive. Chlorine by itself is also very reactive. You put it together, though, and it makes a very stable compound of sodium chloride, which you can put on your French fries. Now let's talk about oxidation numbers in molecular compounds. So a covalently bonded molecular substance does not contain ions. That's the first thing that we have to make absolutely clear. A molecular compound will not contain ions. The elements involved are not fully losing electrons or gaining electrons. They are sharing electrons. But yet, in most cases, the atoms behave as though they possess charges. And we're going to call those apparent charges. So in some situations, we can assign oxidation numbers to the nonmetals that make up these molecular compounds and see that they are basically neutral. So for example here, we know that hydrogen is going to be +1. That sulfur, if we look on our table, if hydrogen is positive, sulfur has to be -1. So +1 times 2 gives me +2. Sulfur, there's an assumed 1 here, so -2 times 1 gives me -2, so the whole thing is equal to 0. Therefore, this is a stable compound that's electrically neutral. Let's start talking about some of the rules. The first one we're going to look at is oxidation numbers in free elements. So the oxidation number of every atom in a free element is 0. How do we define a free element? A free element is an element not combined, that's important, not combined with another element in a compound. So it's freestanding, it's not combining with anything else. So some examples that we might look at here. For metals, this would be like magnesium or copper, or calcium, iron. For nonmetals, these would be your diatomics: oxygen, hydrogen, chlorine, fluorine, nitrogen, iodine, and bromine. And then there are some nonmetals that would be freestanding by themselves: carbon, silicon, phosphorus, sulfur, any of those nonmetals that might be able to stand alone. Each of these is an oxidation number of 0 when found alone in a chemical reaction. And when we start talking about things like synthesis reactions and single replacement reactions, this will make a lot more sense. Now let's talk about oxidation numbers and neutral compounds. This is where we really start applying our understanding of oxidation numbers and how we see the compounds being electrically neutral. So in a compound, the algebraic sum, in other words, you're adding them together, of the oxidation numbers must be 0, since all the compounds are electrically neutral. In other words, they're not carrying an overall charge. So let's look at some examples here. LiCl, the only charge that lithium can be is +1. Chlorine is -1. So +1 and -1, therefore my overall charge will be 0. For hydrogen, there's 2 hydrogens here, so each hydrogen will have a charge of +1. +1 times 2 gives me an overall charge of +2. Oxygen, if we look on our periodic table, we see that's -2. So the overall charge between +2 and -2, those two are going to cancel each other out. Therefore, the overall charge is 0. Now, what if we go in and we assign some oxidation numbers to these 2 compounds here based on what we know? So every time you do this, you're going to want to make sure that you have your periodic table handy. You're not creating a charge to assign to one of these elements. So the first one is sodium. If we look at our periodic table, the only charge that sodium can be is +1. Hydrogen. Hydrogen can be +1 or -1. The majority of the time, hydrogen is going to be +1. And then for oxygen, the only charge that oxygen that can be typically is -2. -2. Now, there are assumed ones of subscripts for all of these here, but we do not write them into our formulas. But we could look at this and say, well, 1 times 1 is 1, -2 times 1 is -2, and 1 times 1 is a +1. Therefore, when we look at this, the overall charge is going to be 0. Let's look at another one here. Potassium. Potassium is in group 1. The only charge that potassium can be is +1. So 1 times 2, because that subscripted 2 is going with the potassium, so 1 times 2 is +2. The only charge that oxygen can be typically is -2, so -2 times 4 is -8. Whole thing has to equal 0. What's the charge that sulfur has to be? Well, it has to be something that's going to make this whole thing electrically neutral. So therefore, I have a +2, a -8. This has got to be +6. +6, because 2 plus 6 is +8, -8 gives me 0. Now, if someone asks you, well, what is the charge on these particular elements that are involved, you want to make sure, always make sure, that you record your original oxidation states, the original ones, not the ones multiplied by the subscripts, but the original ones. That is important and key. Now let's look at oxidation numbers and ions. The oxidation number of an ion is the charge on that ion, which is basically self-evident, but we just want to point it out. So for example, chlorine ion, Cl-1, the overall charge is -1. A copper ion has an overall charge of +2, therefore the charge has to be +2. But things get sort of interesting when you start working with polyatomic ions, and we've talked about polyatomic ions before. These are the ions that are made up of a number of different elements, poly meaning many, atomic meaning atom. So in a polyatomic ion, the sum of the oxidation numbers of its component atoms must equal the net charge on the ion. For example, the sulfate ion, SO4 - 2. This is not an electrically neutral compound. The overall charge has to be -2 because that's what we see in the upper right hand corner here. In an ammonium ion, NH4+1, the overall charge is going to be +1 because we see this +1 up here. Now that is not the individual charges of the elements involved. We can still go back and assign those. These are the overall charges on the polyatomic. Now let's look at some common oxidation numbers. Oxidation numbers are charges that are going to hold constant no matter what happens. In most compounds, hydrogen has an oxidation number of +1. Also, in most compounds, oxygen has an oxidation number of -2. Group 1 elements will always be plus 1. There is no exceptions to the rule here. All group 1 elements will be plus 1. Same goes for group 2 elements. All group 2 elements will always be plus 2. And the oxidation number for fluorine will always be minus 1. So let's look at this example down here. And this is also brings in our first encounter with parentheses and how important they are. So if we look at calcium, we know that calcium is a group 2 metal. Therefore, the only charge that calcium can be is plus 2. Plus 2, and there's an assumed 1 right here. So positive 2 times 1 gives me plus 2. Now, oxygen is going to be minus 2. And hydrogen is going to be plus 1. How do we work with parentheses? Well, remember, with parentheses, we basically think of the distributive property. And another thing that you need to keep in mind is that this OH here represents a polyatomic, and that polyatomic is hydroxide. So when we think about this hydroxide polyatomic, we know that there is an assumed 1 right here and an assumed 1 right here, down by the hydrogen. So when we look at this, we'd say, all right, 1 oxygen, so that's a negative 2. But remember, this 2 right here is distributive. So this 2 is basically going to make this 1 a 2 and this 1 a 2. So really, what we're having here is negative 2 times 2 gives me negative 4. And positive 1 times 2 gives me plus 2. And this makes sense because when I look at this, I have positive 2 minus 4, positive 2. They all negate each other, so the overall charge on the compound will be 0. So you have to be really careful about the parentheses and make sure that whatever subscript is on the outside is distributing through. Now let's look at some exceptions to the rule. Probably the most common exception that you'll encounter in Regents chemistry is hydrogen. So in most compounds, hydrogen has an oxidation number of plus 1. If I had to make a choice, 99.9% of the time, it's going to be plus 1. The only exception to this rule is when hydrogen forms a compound with a metal. It's going to have an oxidation number of minus 1. Because remember, when you look at your periodic table and you look at the little square for hydrogen, both oxidation states are listed, plus 1 and minus 1. So again, most of the time it's going to be plus 1. But when you're working with a group 1 metal or a group 2 metal or a metal like aluminum, those are constant. So when you're in those situations, you're going to have to follow what we see in these examples down below. And those situations where you have a group 1 metal or a group 2 metal and hydrogen, those are known as metal hydrides. And you have to be really careful here because hydride looks a lot like hydroxide, but they're not the same thing. If I was to look at this example right here, this example is KH or potassium hydride. If I was to assign oxidation numbers, potassium would have to be plus 1 because it's a group 1 metal. Therefore, as a result, hydrogen has to be minus 1 because 1 minus 1 gives me 0. Same thing over here. Strontium is a group 2 metal. So strontium is going to be plus 2. Hydrogen is going to be minus 1. I think about my subscripts here. There's an assumed 1 right here. So 2 times 1, that gives me plus 2. Negative 1 times 2 gives me negative 2. And the whole thing is going to equal 0. The other exception that you should be aware of deals with oxygen. Now again, in most compounds, oxygen is going to have an oxidation number of minus 2. But on rare occasions, we might find oxygen having an oxidation number of minus 1. We find this in situations called peroxides. The peroxide that you're probably most familiar with is hydrogen peroxide, and that has a formula of H2O2, where in this case, hydrogen still has to be plus 1. So 1 times 2 gives me plus 2, and now oxygen has to be minus 1. So minus 1 times 2 gives me minus 2, and the overall charge is going to be 0. So again, this is an exception to the rule. We don't see it all that often, but there is the cases where oxygen can be minus 1. Now let's take some time and do some practice. So let's go through and do this top one together, and then I want you to stop and try doing A through F on your own. Now, just to point out, it says S in H2SO4. Your best bet is to go through and assign oxidation numbers to everything, but most likely the element highlighted will be the one that will be the most difficult to find. So let's just do one more practice together. So in the compound Al2O3, aluminum has an oxidation number of +3. Show that the sum of the oxidation number totals is 0. So the first thing that we're always going to do is write out our formula. So Al2O3. And then they tell us specifically that aluminum has a charge of +3. So I'm going to put that over the top. So +3. So +3 times 2 gives me +6. That means the oxygen has to be -2 because -2 times 3 gives me -6, and the whole thing will equal 0. So there's an example that you can use to work from. So stop, take a moment, practice these, and come back and check your work. Welcome back. Let's see how you did. So sulfur in H2SO4. I'm always going to start by assigning oxidation numbers to the elements that I absolutely know. So I know that hydrogen is going to be +1, and oxygen is going to be -2. So +1 times 2 gives me +2, -2 times 4 gives me -8. The overall charge is going to be 0. So +2 -8, this means this has got to be +6. I check my reference table because I'm looking at sulfur. Sulfur has the ability to be +6, so sulfur has to be +6. Now let's look at Fe and Cl and FeCl3. Well, this is sort of interesting here because you have a transition metal, which you know has to be positive, and a nonmetal, which you know has to be negative. Iron has a number of different oxidation states. It can be +2 or +3. One way that you can figure this out, what the charge is on iron, is just by reverse crisscrossing it. So this 3 had to come from the Fe. So if I take this 3 and I bring it back, this Fe has to be +3. So Fe, there's an assumed 1 right here. So +3 times 1 gives me +3. I need this whole thing to equal 0. Therefore, this has to be -3. I know chlorine can be -1. So -1 times 3 gives me 3. So that's the charges of both of those elements in that compound. Now let's look at a problem that's a little bit more advanced. Na2Cr2O7. They all have oxidation numbers. Na is in group 1, so it's going to have a charge of +1. Oxygen is going to be -2. So +1 times 2 gives me +2. -2 times 7 gives me -14. The whole thing has to equal 0. So when I look at this, +2 minus 14, this has got to be +12. What number times 2 will give me 12? And I know that is +6. So I go back, I check my reference table. Chromium has the ability to be +6. Therefore, I know I'm right. Now let's look at a polyatomic ion. This is a situation where it's not going to equal 0. In this case, our overall charge is going to be -3. So I have PO4 -3. I'm going to start with oxygen because I know that oxygen is going to be -2. So -2 times 4 gives me -8. My overall charge is -3. Therefore, the only number this could be is +5. So phosphorus has to be +5 because +5 minus 8 gives me -3. Now, let's look at one of the trickiest ones out there because in almost every, in every single one of these situations, it seems like our first number is always a positive number. And as we do a lot of practice with these, you get into the habit of thinking to yourself, well, the first one's got to be positive. The first one's got to be positive. But if you look at ammonia here, NH3, and you say to yourself, well, nitrogen's got to be positive and hydrogen's got to be negative. Well, not the case, because hydrogen can only be a -1 ion if it's with a metal, and nitrogen is a nonmetal. Therefore, hydrogen has to be +1. There's really no other option. So +1 times 3, that gives me +3. The overall charge is going to be 0. Therefore, nitrogen has to be -3. -3, -3, -3 plus 3 will give me 0. And if you think about that, That makes sense. Nitrogen has 5 valence electrons. It wants to get its full octet. It would rather share 3 electrons with hydrogen to get that full octet. So it's going to attract those electrons to itself. So more likely to be negative than positive. And then finally, CHS, cesium hydride. This is where we find our exception to the rule for hydrogen, where hydrogen will be -1 because cesium is a group 1 metal, so cesium has to be +1. Therefore, it's going to be 0 and an overall electrically neutral compound. So what did we learn in this tutorial? Well, we went over what are oxidation numbers. We looked at different oxidation numbers in ionic compounds, oxidation numbers in molecular compounds. We looked at oxidation numbers in free elements and the rules that accompany that. We looked at the rules that deal with oxidation numbers in neutral elements, oxidation numbers in ions. We looked at some common ions and some exceptions to the rules. And finally, we did a little bit of practice at the end. Need more help? Feel free to contact me. Have a great day.